So we're moving into chapter 7 of the animals section. The little sign says invertebrate taste test, right? We're vertebrates, we have backbones. Not even a phylum, just part of a phylum. And yet, very commonly, animals are divided into vertebrates and invertebrates, which is all the stuff we've done so far, and the next two phyla that we're going to do. I call it vertebrate chauvinism. And people are not that interested in invertebrates. When I was studying to be an invertebrate zoologist, I was the only person in that part of the graduate school, as opposed to 20 or 30 people in the vertebrate side. That's okay. Our guys are more important. So there's the bird, and it's saying, nope, I don't like that at all. Too many legs. We're going to do arthropods. Arthropods typically have lots and lots and lots of legs. Jointed legs, jointed feet, that's where arthropod, the name, comes from. So, arthropods. It's a D. There's a little group called the velvet worms, the oncophorans. And they kind of superficially look like caterpillars, but they're not. And they have some features that are very similar to segmented worms and some features that are definitely more similar to arthropods. And they are probably what's left of a bridge group between the two. And there are definitely segmented worm features in the arthropods. So they're sort of from the segmented worms. They're just a holdover of things that are still there. So the segmentation is there. It's sometimes pretty obvious and sometimes not so obvious. The ventral double nerve cord is there. A lot of the stuff that we've had all along is there. You've got bilateral symmetry, encephalization, and a long tube digestive system. So that stuff has just been going right along. One of the major groups of the arthropods also has antennae and mandibles. The other subphylum does not. This is a phylum, remember. Couple of things. Okay, where's that? Sorry, I lost my train of thought. That happens more as you get older. So these have body sections, they have legitimate legs, articulated legs, and they still have the chitin, that hard material, but they use it for an outside, now I know what I'm supposed to put here. Open circulation. Let me move this and I'll show you. These animals are essentially hollow. They have a circulation system, so it requires a pump. So there's a heart, and it's got outflow, but the outflow eventually just goes into the hollow spaces of the body. It has intake, sometimes from tubes, but very often from openings along the sides of the hearts. Heart's usually on the dorsal side, as opposed to us where our heart's on the ventral side. And the blood just kind of circulates, kind of slooshes around the body. Digestive system running through, it's picking up nutrients, it's picking up waste materials, it's pretty efficient at clearing those things out. It circulates oxygen from various sources, but if you need oxygen, if you have high oxygen requirements, it is not great at circulating oxygen. And so in animals that have very high circulation, very high oxygen requirements, that are very active, especially things that can fly, there's a supplementary breathing system in a lot of them that helps get oxygen to the muscles that really need to be working all the time. But you do find we have a closed circulation system. The segmented worms have a closed circulation system. A lot of the groups have kind of a combination. Mollusks have some tubes that blood runs through and some what are called sinuses, open spaces that blood goes through. The next group on our branch of the family tree, the echinoderms, have some tubes. We don't even know really why, but mostly the blood just slooshes around inside of them, an open circulation system. So really just us and the segmented worms have lots and lots and lots of tubes. Big deal here. The segmented worms have a hydrostatic skeletal system. Those donuts for each segment are full of fluid that pushes against the muscles when the muscles contract, gives the muscles something to pull against. These guys have an articulated skeleton on the outside as opposed to our articulated skeleton on the inside. So we're going to give you a nice little table. You can be figuring this is going to be on an exam. So their skeleton that the muscles pull against, the rigidity, the anchor points are on the outside. It's like a suit of armor. That's one of the big differences to start. If you've got your hard parts on the outside, sorry, I just stepped on, I guess, an old eraser. Then you're pretty well protected. Now, our hard parts are surrounded by muscle. It isn't protecting them. We do fiddle with our endoskeleton a little bit to make it protective. We put it around our brain, right? This is not really a skeletal element. The only thing that articulates is your jaw and where your head connects to your backbone. There's a bunch of bones in here. They're all zipped together, and they're primarily protective. You can make the same case for a rib cage being somewhat protective. It's really more for breathing, but it's somewhat protective of our internal organs. But for the most part, our soft parts are around the outside of our hard parts. The hard parts are not particularly protective. Like a suit of armor, say you were the most protective parent in the world and you wanted your kid in a suit of armor. You were Tony Stark and you can make a really good suit of armor. So you get your toddler, your 3-year-old suit of armor. Well, like buying shoes for your kid, you don't get one that's really snug on them. You get them something big that they can grow into. Because the thing is, eventually they're going to grow into the armor, And then in order to continue to protect them and allow them to grow, you're gonna have to get them a new suit. You're gonna get them out of the old suit, get them a bigger one, and give them a new suit to grow into. That's what happens with the exoskeletons, is that once they're solidified in place, you've only got the room that you had when you started. So typically their shed is called molting or ecdysis. And so the animal finds a protected place, secretes chemicals between its skin and the skeleton to loosen the skeleton up, cracks the skeleton, usually along the back, and then has to get all of its parts out of the old exoskeleton, which is not easy. Think about how complex these animals are with their toes and their antennae. There's a reason why insects only have wings when they're adults, because they couldn't really get the wings out particularly easily. When they do form their adult form, they crack a pupal form, which is pretty simple. That you can get the wings out of, and then you push fluid into them to straighten them out, and then they have to harden. So what happens is they crack, they get out, they puff up. Sometimes they take in water, sometimes they puff up with air, but they grow very quickly while they're soft. And then they put a new skeleton around the expanded version, and then they have to grow into it. So if you're looking at growth in an endoskeleton, there may be spurts, but the growth is fairly even. For an exoskeleton, once it's in place, it doesn't grow. And then you shed it and puff up and grow really fast, and then it doesn't grow for a while. So growth in an exoskeletal system looks like a staircase. Endoskeleton, not so much. All those horror movies showing giant insects or giant spiders or giant whatever doesn't work. Is that a suit of armor covers your whole outside. It is heavy compared to a support system that's on the inside. And the bigger you get, the heavier it is in proportion to what you're capable of moving. Your muscles just can't keep pace as they get bigger and bigger and bigger. That's why things with exoskeletons are small. The only large examples you can find are in the fossil record, and they lived in the water where they had some water support, some buoyancy to be able to allow them to move around. You get onto land, and you're not going to get a spider the size of a car. It just wouldn't be able to move. Whereas with our skeleton on the inside, especially hollowing our bones out, allows us the potential to grow huge. And all of the huge animals you can think of are all animals with endoskeletons, the dinosaurs, who may have had legitimately hollow bones like birds do, which allowed them to get really big. In our group, the only really big things also have buoyancy in the water, things like whales. But potential for size, very much a part of an endoskeleton and not an exoskeleton, even though it says leverage. I left the letter out. When you're pulling around a hollow tube, sending the force around the corners is a pretty simple pulley system. And more of the pull exerts on what you're pulling. Whereas for us, we have to kind of pin our connectors down so that when you bend your arm, the muscle here doesn't connect straight across. It doesn't require stretching of your skin. And so you lose some of the pulling ability in an endoskeleton just because it's of the way it's set up. So an exoskeleton is proportionately stronger, but that's misleading. When you hear you know, in every superhero based on an exoskeleton animal, is that they have the proportionate strength of a spider or an ant or, I don't know, a centipede. That's more, that proportionate strength of an ant or a spider is more related to the fact that they are very small. And when muscles get bigger, they don't get proportionately stronger. You double the size of a muscle, you don't double its strength. So as we get bigger, we get proportionately weaker. I mean, a mouse is proportionately stronger than a human is. But, you know, Mouse Man just never caught on. Mighty Mouse. But he was a mouse. But, so that makes an ant, relative to its size and weight, a particularly strong animal. But that's because it's got little bitty muscles that are proportionately strong because they're little bitty compared to a really big muscle. But they also have better leverage. I'm trying to make these shorter. We're going to stop there. Then we're going to do a fairly short one for one of the subphyla, and then do a somewhat longer one for the other subphyla.